In section 7.2, we're looking at some more identities. We're going to check out the cofunction and the double and half angle identities. Our objectives are to use cofunction identities to derive other identities, to use double angle identities to find the function values for twice an angle, to use half angle identities to find function values for half an angle, and to simplify trigonometric expressions using double and half angle identities. Starting with cofunctions, a quick review of cofunctions from chapter 6. You might recall that the sine and cosine functions are cofunctions of each other. What does this mean? Consider how the graphs of both on the same axes are shown. So the sine of x function is shown here. And the cosine of x function is the one that's dotted. I'm going to highlight that one in pink here. Cofunctions meant that two angles that added up to 90 degrees had the same function, had opposite function values. So, for example, it meant that sine of 30 degrees equals cosine of 60 degrees, right? Because those two angles are complementary. So it meant that they had opposite equal function values for complementary angles. So sine of an angle equals the cosine of the angle's complement. That's what cofunctions means, right? Sine of 30 equals cosine of 60, and whatever the angle is, the sine of that angle equals the cosine of the complement. So I wrote mine in terms of degrees instead of radians, but we can go with that same idea. If we think about pi fourths, pi fourths is its own complement. There we go. It's its own complement, and therefore sine and cosine are going to be equal, since pi fourths plus pi fourths adds to pi halves, or 45 plus 45 adds to 90. Also, 0 and 90 itself are going to be complements. So here we go. The sine of 0 has to match up with the cosine of 90, and they're both the same value. And similarly, the sine of pi halves has to match up with the cosine of 0. They're both equal to 1. And I can see this at many other points along the graph as well. If I imagine where pi sixths is, that would have to be equal to the cosine's value at pi thirds, and those are the same heights right there as well. Okay, so two angles that are going to be complements have a sine of the angle equals cosine of the complement. To write that a little more formally, we can look at the cofunction identities below. So the cofunction identities say that the sine of pi halves minus x is equal to cosine of x, and vice versa. The cosine of pi halves minus x is equal to sine of x. This right here is exactly what we set up here in words, that the sine of an angle is equal to the cosine of the complement. So the complement of the angle is going to be pi halves minus the angle. Okay, so inside this angle right here, that is just the complement. Okay. All right, so these are our cofunction identities. We have them for sine and cosine. We also have them for tan and cotan. Tan and cotan are cofunctions as well. So the tangent of an angle is equal to the cotangent of the complement and vice versa. And then similarly for secant and cosecant. The cosecant of an angle is equal to the secant of the complement and vice versa. So we already knew that these functions were equal for complementary angles. Now we've just got them expressed as identities here. Let's take a look at how this impacts our next page. We're asked to use a previous identity to find a new identity for the sine of x plus pi halves. This is not a cofunction because this is now a sum. So x plus pi halves is going to be an angle that's larger than 90 degrees. They're not complements. But I have something that looks a little similar. Instead, though, it is an addition. And so I'm going to be able to go back to the previous section and my sum and difference identities. When I have additions like that, I'm going to be able to use these to build a new identity where one of those angles is known. So this here being an addition is going to be using the sum identity. So for sine of x plus pi halves, we're going to have the u being x and the v being pi halves. So sine of x plus pi halves is going to be equal to sine of u, so that's going to be sine of x, times the cosine of v, so the cosine of pi halves, plus the cosine of u, so the cosine of x, times the sine of v, so that's the sine of pi halves. That's just the sum identity for sine. Now I can evaluate the cosine of pi halves and the sine of pi halves since that's a numeric angle. On the unit circle, I know that pi halves is right here, and that's the ordered pair 0, 1. So the cosine value is going to be 0. And the sine of pi halves is going to be 1. So this is going to be equal to cosine of x. So our new identity, I'm going to rewrite the left-hand side, is that sine of x plus pi halves is equal to cosine of x. So for the sine function, this looks very similar to the cofunction identities from the previous page. The cofunction identities would have said that sine of pi halves minus x is equal to cosine of x. It turns out through the sum identity that the sine of x plus pi halves is also equal to cosine of x. Let's see if the reverse is true. Let's see what happens for cosine of x plus pi halves. We are again going to use a sum identity for cosine this time. Cosine of x plus pi halves is going to be equal to, make sure you take a look at your sum identity for cosine, cosine of u, cosine of v, minus sine of u, sine v. We are again using a u of x and a v of pi halves. So this is cosine of x, so cosine of u, which is cosine of x, cosine of v, so cosine pi halves, minus sine of x, sine of pi halves. We're still looking at that angle pi halves here, whose ordered pair is 0, 1. So we've got cosine of x times cosine of pi halves, which is 0, minus sine of x times sine of pi halves, which is 1. So it's equal to the negative sine of x. So cosine of x plus pi halves equals the negative sine of x. So this is an instance where the sum identity for cosine of x plus pi halves is not exactly the same thing as the cofunction identity on the previous page. It's a new identity. And then use the two previous identities to find a new identity for tangent of x plus pi halves. If I use the two previous, I know that tangent of anything, including tangent of x plus pi halves, is equal to sine of that same thing, sine of x plus pi halves, divided by cosine of that same thing, cosine of x plus pi halves. That's one of my basic identities. And I know from example 1 that the sine of x plus pi halves is equal to cosine of x, and the cosine of x plus pi halves is equal to negative sine of x. And so cosine of x divided by negative sine of x is equal to negative cotangent of x. So my new identity is going to be tangent of x plus pi halves is equal to the negative of cotangent of x. So again, another identity for tangent of x plus pi halves equal to negative cotangent of x. There are similar co-function-based identities for all 6 trigonometric functions. Secant of x plus pi halves, that would be 1 over sine of x plus pi halves. So I would get 1 over cosine of x, which would be secant of x. Nope, my mistake. I apologize. Let me take that off. I was thinking of cosecant, not secant. I'm used to having cosecant first. That's the one for cosecant. Cosecant is the reciprocal of sine. So I got those backwards. Cosecant here, being the reciprocal of sine, would give me the reciprocal of cosine. So this is the one that would be equal to 1 over cosine, or secant of x. This one in the middle. Secant, that's the reciprocal of cosine. So I would get the reciprocal of negative sine. 1 divided by negative 1 is still negative, so we get negative 1 over sine, which is cosecant. And then cotangent, we're going to get the reciprocal over here. So it's going to be negative 1 over cotangent, which is negative tangent. So again, each of those is another similar identity that can be gotten based on taking the reciprocal of both sides of the previous 3 groups of identities. All right, next we're going to take a look at double angle identities. So we're going to look at a special case of the sum identity, a double angle. What happens if you're adding the same angle to itself? And we'll use the sine identity for our example here. So the sine of 2x is equal to the sine of x plus x, right? That's the basis for our double angle identity. So we're going to set this up where u is x and v is also x. Using the sum identity for sine, that sum identity is sine u cosine v plus cosine u sine v. So that's going to end up with sine x cosine v, which is x, plus cosine u, which is x, sine v, which is x. So sine x cosine x plus cosine x sine x. The order doesn't matter, so it's really 2 of the same thing. I end up with 2 sine x cosine x. So the sine of 2 times x is equal to 2 times the sine of x times the cosine of x. This is the first of our double angle identities. Sine of twice an angle is equal to 2 times sine of the angle times cosine of the angle. Similarly, you can work out double angle identities for both cosine and tangent. So one of the double angle identities for cosine is cosine of 2u equals sine squared u minus, cosine squared u minus sine squared u. And the tangent of 2u is going to be equal to 2 tangent of u divided by 1 minus tan squared of u. The cosine double angle identity can be combined with the Pythagorean identity in 2 different ways. So remember that the Pythagorean identity says that sine squared theta plus cosine squared theta is equal to 1. So if I take a look at cosine squared u minus sine squared u, if I solve my Pythagorean identity for sine, if I solve for sine squared theta, I would have 1 minus cosine squared theta. So sine squared of u is going to be equal to 1 minus cosine squared u. So I would have cosine squared u minus 1, negative, negative, plus cosine squared u. So this comes out to be 2 cosine squared u minus 1. So we're going to write that one in up here as well. This is also equal to 2 cosine squared u minus 1. It's an alternate version of what cosine of 2u is equal to. This one's usually listed on formula sheets with all 3 possibilities because which one you need might depend on what your goal is. If you're trying to get down to a fewer number of functions, this may be your choice. However, it might not be the only choice depending on what function you want. Instead of solving and getting rid of sine, what if we did it for cosine? So if we got our cosine by itself, that would be equal to 1 minus the sine squared u minus sine squared u. So again, solving for cosine squared would be 1 minus sine squared. So I have 1 minus sine squared u minus sine squared u, or 1 minus 2 sine squared u. It's also equal to cosine of 2u. 1 minus 2 sine squared u. So there are 3 different forms of the cosine double angle identity. You'll only know which one you want based on context of a question. Sometimes you might only have a cosine of a squared or a sine squared, and you'll use one of these two. It just depends on context. All right, so let's move on. Additionally, we can make use of the identity tan squared x equals sine squared x over cosine squared x to come up with yet another. So we know tan squared x is equal to sine squared x over cosine squared x. We want to use what we just got up here and do some substituting. So we know that for sine squared x, we know over here, cosine of 2u equals 1 minus 2 sine squared of u. So let's solve for that sine squared of u. To make it positive, let's just add it to the other side and subtract this over. So 2 sine squared of u would equal 1 minus cosine of 2u. And while we're working on this, these are going to be our notes on the side over here. We also know that cosine of 2u is equal to 2 cosine squared u minus 1. So let's add that 1 over here. Cosine of 2u plus 1 is equal to 2 cosine squared u. Now, I don't have these 2's in my sine squared and my cosine squared, but it would be no problem to multiply top and bottom of a fraction by 2 over 2, since that reduces to 1. So we'll do that first. That gives me 2 sine squared x over 2 cosine squared x. And so 2 sine squared x, 2 sine squared u, 2 sine squared x is equal to 1 minus cosine of 2x, and 2 cosine squared x is equal to cosine of 2x plus 1. So let's rewrite this here. The tangent squared x, the new identity we've written here, is 1 minus cosine of 2x. I'm really emphasizing the size of that. I don't want to look like it's cosine squared of x. It's not. It's double angle. Another way to emphasize that would be to use parentheses. It's cosine of 2x. And this identity is typically written with the bottom as 1 plus cosine of 2x. It just has things nice and lined up there. Same thing as we had right here. So this is another identity that we get as a corollary of these two. And in terms of making things simpler, if you had something like tan squared x, you could argue that this has two functions. However, it has a lower power, so it's potentially a simpler function. Depends on what your goal is again. This function, by the way, this identity is called a power reducing identity because we've taken something that has a square down to something that does not have a square. So this is an example of a power reducing identity. All right. And again, it came from making use of the basic identity for tangent and also cosine's double angle identities. Okay. The next topic is on half angle identities. So not surprisingly, we can make use of some of the previous identities to get identities for the half angle. Notice that there is a catch here that we have to be aware of what quadrant the half angle lies in, because the reference angles may lead to sign changes. So on this one, the sine of x over 2 is equal to positive or negative the square root of 1 minus cosine x over 2. That is not a both or an either. It's a you need to figure out whether it's positive or negative based on which quadrant that half angle lies into. So it's not a choice. Same thing for all of these. This is not, it's either positive or negative or both. It's not a both. It's a you figure out which. So you figure out the sign. So plus or minus based on the angle's quadrant. For x over 2 or theta over 2. Okay. All right, so let's take a look. We've got an example. Find the exact value of tangent of 22.5 degrees. That's not a special angle. However, I'm trying to find my calculator. There we go. Clear this. 22.5 is half of 45, and 45 is a special angle. So if I wanted to find the tangent of 22.5 degrees exactly, I would say I know that's the tangent of half of a 45-degree angle. Then I'm going to go to my tangent of half an angle, and we know it's equal to positive or negative, and tangent has 3 possibilities. So I can choose whichever of these I think would be easiest to work with. If I don't have to have the square root in there, probably easier to work with one of these two. The advantage of the square root is that it only relies on the cosine function. And so if I didn't know the sign, then perhaps it would be easier for me to use this one. But for 45, I know both the sine and the cosine, so let's go with one of the other two. I'm going to go with the last one just because it has a single fraction. The denominator is going to make it easier for me to rationalize the fraction. So I'm going to choose to use that last one. 1 minus the cosine of 45 degrees over the sine of 45 degrees. Now, in terms of the positive and negative, I'm going to say it's going to have to be a positive because I know that 22.5 degrees is in quadrant 1. So I know the answer to tangent needs to be a positive. So I'm going to make sure that this becomes positive. So I need 1 minus the cosine of 45 degrees is root 2 over 2 over, we'll talk about sines again here in a second, the sine of 45 degrees, which is root 2 over 2. Okay. We're going to rationalize this because we've got ourselves that fraction on the bottom. So I should say we're just going to simplify this. So we're going to take our entire numerator here, 1 minus root 2 over 2. And instead of dividing by a fraction, we're going to multiply by the reciprocal, 2 over square root of 2. If we distribute that, 1 times 2 over square root of 2 is 2 over square root of 2, minus square root of 2 over 2 times 2 over square root of 2 is going to be 1. And then let's just rationalize on this part right here because it's going to clean this up. If I multiply by square root of 2 on top and bottom, that gives us 2 square root of 2 over 2, and then our 2's reduce. So this number is going to simplify to the square root of 2 minus 1. Now, talking about sine, let's make sure that that value is a positive value, and we'll check our answer here. So square root of 2 minus 1 is a positive value. We were hoping for a positive value. That sounds good. And let's go into degree mode. We're going to do the tangent of 22.5. Those decimals match. So this is the value in simplified exact form for the tangent of 22.5 degrees. Okay. I would have gotten the same answer using any of these formats. Biggest reason I chose the last one is because I knew both sine and cosine of 45. And I knew that if I had a single fraction in the denominator, I could flip and multiply by it. If I had 2 things in the denominator, I would have had to get common denominators and add before I could do that. So doing that division, I knew the answer was going to be root 2 over 2 from the sine value, so I could predict that fraction down here would need to be flipped. And so if you can look ahead a few steps, it can help you select which of the formulas for tangent to use. Okay. We're going to find the exact value now of tangent of 5 pi 12ths. So 5 pi 12ths is, I think we used that value as a sum angle earlier, but it's also half of 5 pi 6ths, and a pi 6th measure is going to be on the unit circle. So we're going to do this one in terms of a half angle identity here. We're going to find that there are going to be some angles like this one that are both sums and halves of things. We can use multiple ways. This one is 5 pi sixths divided by 2. And let's just make sure 5 pi sixths is somewhere on the unit circle that I know something about. So on the unit circle, 1 pi sixth, 2 pi sixth, 3 pi sixth, 4 pi sixth. This is where 5 pi sixths would lie. And it's going to have ordered pair. The x-coordinate is going to be negative root 3 over 2. It's longer than it is tall, and its height is going to be positive 1/2 since we're in quadrant 2. The x's are negative, the y's are positive. So that's the ordered pair for this. So I know both the cosine and sine values for the angle 5 pi sixths. So I can use either of these. Let's see. Based on the fact the cosine value is the one with the square root of 3 over 2, I'm not going to want to use that multiple times, and I'm not going to want to add 1 to it on the bottom to get a common denominator. I'm going to want to work with the one that has the sign in the bottom. Again, it just is going to be a little simpler for us. So we want this to be equal to positive or negative 1 minus the cosine of 5 pi sixths over the sine of 5 pi sixths. Now, I know where 5 pi sixths is, but I need to know where 5 pi twelfths is. So remember that this right here is pi halves, and 5 twelfths is less than a half. A half would be 6 twelfths. So somewhere around here is the original angle, 5 pi twelfths. And that angle is going to be in quadrant 1. So once again, the angle needs to have a positive tangent value because it's in quadrant 1. The larger angle is in quadrant 2, but the angle that we're trying to find the tangent of is in quadrant 1, so the result needs to be a positive. Okay, so we're going to be positive 1 minus the cosine of 5 pi sixths, which is negative root 3 over 2, over the sine of 5 pi sixths, which is a half. So I've got 1 plus the square root of 3 over 2 when I take those two negatives and turn them into an addition. And then I'm going to multiply by the reciprocal, so 2 over 1. And this comes out to 2 plus the square root of 3. And I distribute the 2. Okay, so let's check that. Let's get the calculator now into radian measure. Let's go ahead and clear it as well. We want to check that the tangent of 5 pi over 12 is equal to 2 plus the square root of 3. Yes, it is. So we've got our exact value for the angle that is half of a known angle, the 5 pi 6, which is a known angle. Okay. As we mentioned before, it is also completely possible to evaluate the 5 pi 12s by adding, isn't it pi 6 and pi 4? So we did that before in the last section. So you could also have used the sum identity for this, or the half angle. They both would give you the same answer.